Where's the rest of the class?
I've reminded them they will be joining us as we are ongoing.
Okay. So Moses, you can see the presentation on the screen.
Yes, yes. It's
Okay.
visible.
So this is the shunt regulator that we analyzed in the last class. Starting from the left, R3, and the Zener diode is used to design our reference circuit. The op-amp is our error amplifier. R1 and R2 is the output sampling element to give the error amplifier some feedback of what's happening at the output. The control element over here is the transistor, which is connected in shunt to the load, hence the name shunt regulator. And then you had your load. Our unregulated input is V1. So we came to the conclusion with equation 16 that V naught is just Vz into bracket 1 plus R1 divided by R2. And from this result, the following inferences could be made, or the following deductions could be made. Number one, that V naught is independent of is only dependent on the value of Vz, R1, and R2. That is the terms given independent of RL and V1, because we don't see RL and V1 in equation 16. Of course, this only applies when the circuit is functioning properly. You can put the circuit into some extreme conditions. For example, if the input voltage V1 is 0, then we don't expect any output. Also, if you short circuit the output, then you don't expect this equation to occur. This equation 16 to be satisfied. The other inferences we can make is that V naught is V1 minus the drop across R1. Across R. R is that series resistance we put. If you look at this circuit over here, This is this R. So the currents passing through R is I2, I shunt, and IL. So we can say V1 minus the drop across this R will give you your V0. So that's another way of putting at it, looking at it. So the third inference, V0 is V1, our input voltage, minus the drop across that resistance R. And the drop across that resistance R is R into I2 plus I shunt plus IL. And from equation 3, if IL is equal to 0, means you've not connected your circuit to any load, then equation 3 becomes V0 is V1 minus R into I2 plus I shunt plus 0, where 0 is supposed to be substituted for IL. Also, when IL is equal to IL max, means the maximum current that can pass through through the load, then we can substitute it in equation 3 and get that V0 is V1 minus R into brackets I2 plus I shunt plus IL max. Now, if the circuit is working properly, both equation A and equation B must apply, because in the case of B, it's just applying the maximum current. So I've said for equation A and B to be the same, it means for in part B, I shunt must be equal to 0. And IL max is equal to I shunt. And therefore we can write that V0 is V1 minus into brackets R I2, I shunt is equal to 0. And this should be actually IL max. There's a printing mistake over here. Should be IL max. Actually, the way this circuit works, normally you design it such that at the correct voltage that you want, I shunt is equal to IL. As the load current increases, I shunt decreases, such that the drop across this R is constant, and therefore the output voltage is constant. And therefore, if you remove the load, IL is equal to 0, then all your current will be passing through this I shunt, and I shunt will be I shunt max. On the other hand, if you are drawing the maximum current for this circuit, then I shunt is equal to 0, and IL is equal to IL max. So this tells me that I shunt max is the same as IL max. All that happens is that the current is being, as the load increases, current is taken away from I shunt. As the load current decreases, I shunt increases. That is how this circuit works. Now let's consider the efficiency of this circuit. When you're designing power supplies, efficiency is very, very key. Any power supply circuit, be it a series circuit, be it a shunt circuit, be it a switch mode power supply, efficiency is very, very important because the power lost in the circuit will give rise to heating of the components inside. And the heat always destroys the components inside. So normally we want to design a circuit which is as efficient as possible. So let's consider the efficiency of this circuit. Efficiency is normally defined as power to the load, this PL, divided power coming into our regulator, which is P in times 100. That's how we define efficiency. Now, power to the load is IL into V naught. Power coming into our regulator circuit is, if we just look at this circuit over here, I've neglected this I1. If you want to be very critical, you can include it. But this current is normally negligible. Normally, we just want it to be able to bias our reference circuit so that it gives us a stable voltage VZ. So since it's normally a very small current, I can neglect it. Even this current I2 is normally quite small. But I've included it in the circuit. So the currents going into our regulator, if you neglect I1, is mainly I2, I shunt, and IL. So these currents will pass through this resistance, capital R. So power going into our regulator will be the voltage from this point times into brackets I2, I shunt, and IL. So that's what I've used over here. So here I'm considering the no load efficiency. No load efficiency means nothing is connected to the output circuit. But this equation over here, PL over I in times 100, is the definition of efficiency in general. We also give it the unit meter. So sometimes we write meter is P to the load over power in times 100. So this will give you Newton percentage. So in general, we get efficiency is IL for this circuit, IL V naught, because IL V naught is power going to the load, all divided by power in. Power in is voltage times current. So I've quoted the currents first. So we got I2, I shunt, IL into V1 times 100. But since it's a no load efficiency, IL is equal to 0. So this V naught missing over here. All divided by I2, I shunt, and IL is equal to 0 in these terms into V1 So the no load efficiency of this circuit is 0% because the numerator is 0. Now I've considered another case here, efficiency when IL is equal to I shunt. So this is normally the normal operating conditions of the circuit. We want IL to be equal to I shunt at our design voltage, so that when the load increases, it can take some current from I shunt. When the load decreases, some of the load current can go back to I shunt. So I also have some typing errors here, which are corrected. So from equation that efficiency is P load divided by P in times 100%. But in this case, IL is I shunt. So I substitute here in the numerator. I'll just put I shunt in the numerator because IL is equal to I shunt into V naught, all divided by, look, the brackets are also missing here, all divided by, sorry, all divided by I2, which is this first term over here, plus I shunt. And now IL is not equal to 0, but IL is equal to I shunt. So in the denominator here, you'll have 2 I shunt. In the denominator here, you'll have 2 I shunt. Now, since I2 is normally very small, this equation, this I shunt in the numerator can cancel the I shunt in the denominator here, and this becomes a half. So this first equation is just 1/2 V naught divided by V1 times 100%. Okay. And then instead of V naught, we derived V naught as equal to Vz into brackets 1 plus R1 over R2. And therefore, the efficiency of the circuit when I shunt is equal to IL is Vz into brackets 1 plus R1 over R2, all divided by 2V1. For those who've forgotten how we derive V naught, we can just look back here. Equation 16 is V naught. V naught is Vz 1 plus R1 divided by R2. So in this derivation, I've said that I2 less than I shunt. Normally I2 is very small. So that's why I've been able to ignore it and say it's just approximately 1/2 V naught over V1. Now let's consider some of the advantages of this scheme of implementation of a DC regulator. Number one, it is short circuit proof. We look at this circuit over here. If you short circuit it, you put a short between the output here will be 0, and all your devices will be protected. All your devices will be protected. Because your transistor will be protected because the voltage across the collector is 0, so no current is going to flow through it. Your op-amp will also be protected. Remember, op-amps, there's a part which is missing over here. For those of you who use op-amps in the lab, Normally pin number, I think it's pin number 6 and 4 is normally connected to the supply. Let's see, let me just show you. This is a Texas Instrument op pump. So actually it is using pin number 7. If you look at here, pin number 7 is VCC. Pin number 4 is one which is connected to. So number 6 is normally output for this op pump. So you got to look at the data sheet. So pin number 7 is positive VCC, pin number 4 minus VCC, or you can put pin number 4, 0 volts, and pin number 7 to be your VCC. Op pumps, you can use single rail power supply, or you can use double rail power supply, but you got to bias it correctly. So they're not included over here. You've got to be included, they'll be here. So it will be normally a pin over here. So this will go to maybe that part, this will go to this part. So when somebody short circuits, the load, then the supply voltage of the op amp is 0, its drive is 0, the transistor is driving the voltage across it, the collector emitter is 0, so you can't damage the circuit. So that is one big advantage of these shunt DC voltage regulators. Then it's got a very fast response to input transients. It's got a very fast response to input transients. Okay, so that means for just to draw it over here again, supposing, since I don't, you got your R, and then you got your op amp over here, you got your R1, you got your R2. This gives feedback, and then, your control element, and then you got your load. So what I'm trying to say over there, if this voltage, supposing it was maybe constant and regular voltage, then it suddenly spikes up to something else, then this spike will appear here suddenly. This spike, because this resistance is not very high, so it doesn't have any time constant. So whatever is felt over here will be felt over here immediately, and whatever is felt over here will be divided by R1 and R2 at almost the same instant of time. And the correction will be done almost immediately. Of course, that depends also on the speed of the op amp. We have different types of op amps. We have op amps which are slow. We got op amps which are fast. We have things like comparator op amps which are very fast, which are used in digital circuits. So it's just like transistors. You have transistors which are slow. For example, you have the audio frequency transistors, like the BC107, 108, 109, etc. Then you got, after that, you got the RF frequency transistors, like the BF 194, 195, etc. Then you got the very fast ones, which can work up to microwave frequency, like the like the BFY90, etc. They can work up to gigahertz. Okay, so as long as you've done your design properly and chosen the correct transistor, your circuit will be very fast. But here we are comparing them with the other techniques of implementation of voltage regulators. We are comparing it with the series regulator, which is actually our next topic, and the switch mode regulator. Now, switch mode, as I said, that would be assignment. So you'll have to study that one. It's actually very simple. So it's got a very fast transient response. A transient is when the voltage changes suddenly. We call it a transient. Then it does not suffer from RFI, means radio frequency interference, or EMI, means electromagnetic interference emissions. The devices are not operated as switches. And then it's low cost due to the simple circuit implementation and lends itself to IC fabrication. Now, the disadvantage of this scheme is that it's got very poor efficiency. Remember, we said that even when there's no load, all the current is actually passing through the shunt device. As you start increasing the load, that is when current is removed from the shunt path and goes to the load path. So this circuit consumes a lot of power even when there's nothing connected to it as the load. Another disadvantage is that it has got a high output impedance. It's got a high output impedance, which I say right here is 1 over H or E in parallel with the R. As this RS over here is actually this R over here. Seeing it's a series resistance to the load is this RS over here. Okay, so if you were to look at this circuit, you got this R, and this is your V1 input. So in this case over here, I'm calling this R to be your RS. And then you got your transistor, which has got an impedance of 1 over HOE. So the output impedance is this resistance. Seen looking back, it's the load resistance it's the resistance that the load sees. And next, the DC output voltage is not absolutely constant because Vz varies slightly with temperature. Now, actually, whenever you use a Zener, all circuits, be it in the series configuration, shunt configuration, or you use it as a reference in a switch mode power supply. Of course, most of the times when you're doing the analysis, we assume that the voltage is constant. But you have to get all the details from the data sheet of the manufacturer. A normal Zener, I got some dynamic resistance because it's a semiconductor junction. And the semiconductor junction, you know that the dynamic resistance always changes with temperature. So the same will apply to the PN junction of a Zener diode. The dynamic resistance is the slope, like for example, for a normal diode with the characteristic of a transistor. The FEE is like this for Zener. It's like that. This is positive, negative voltages. So we use Zener, we bias it, we reverse bias it. So the slope of this curve over here will give you the dynamic resistance because this axis is voltage, V diode. And this other axis here is current. So the slope of it will give you the dynamic resistance. and that dynamic resistance changes with temperature. Dynamic resistance becomes smaller, just like in the case of a normal diode as the temperature increases. Okay, so this condition number 3 is not specific to only the shunt regulators, but any regulator whereby you have a Zener diode. Number 4 is that V0 must be less than the input. This circuit will only work when the output voltage is less than the input voltage. And lastly, and this actually also does not apply only to this circuit, it will also apply to some of the other implementations that we shall see, apart from switch mode power supplies. And then lastly, I've said there's no total isolation between the input and the output. Okay, because the input is connected to our regulator and then connected to the output. So if you put a resistance meter between the output and the input, you'll always find a connection. That's what that means. So let me conclude by saying we've done a lot of work on this circuit, but because of its poor efficiency, it is rarely used. It is rarely used. But we have some applications. Number one is low output power supply, low output power supplies. Like if you want a power supply maybe up to say 50 milliwatts. For example, we use it in this niche. Normally we use them. Another shunt regulator, which I've not told you, but we use all the time, is here's in a diode. This is a regulated power supply, and this here V0. Of course, you got to design this R to be appropriate. So this also a shunt regulator. Well, here V0 is actually VZ. So all we are doing is we are using the characteristics of a Zener and we bias it at a particular current, say this current over here. And when the load current increases, we'll always ensure the current going to the shunt will be less, so it'll be operating over here. When the load current decreases, here. So let's assume this current is I optimum. And this will be maybe IL min. No, IL max. And this will be IL min. So the current, there'll be a shunt current passing through this. Then there'll be a load current going to the load. So actually, our reference voltage is also a DC shunt regulator, which normally supplies very little current. So we can say that our reference circuit is actually a low power supply. So they can also be used as current sources and current sinks. They can also be used as references for error amplifiers, just as we used it over here. They can also be used as adjustable voltage or current. I think this should be in adjustable voltages or currents. I think there's something missing over here. Adjustable voltages or currents. They should be in linear let me just put across this first. In linear or switching power supplies. They can also be used in voltage monitoring. It can also be used. Now, how do you monitor voltage? If you got a circuit, say the voltage say V0, now they used to you want to drop a very large voltage. Like if your DC voltages are high, like in some switching power supplies, but they get the voltage directly from the mains. So when you rectify it, you get say like 350 volts. But you want to monitor a section of that. So you'll drop a large voltage, you use a high voltage Zener to drop most of the voltage across the Zener so that the current that passes through the circuit. So let's assume this is a very high voltage, say like 340 volts, like if you mains rectify, 340 volts DC, then the current I through the circuit will be V0 minus Vz all over capital R plus R1 to get the current. So the function of the Zener there is to drop most of the voltage. And therefore now, if the voltage increases, the drop across R1 will increase. And this drop now will be a small voltage. And this voltage can be used to monitor how that output voltage is changing. So that you can either trip an alarm if it's in a circuit that powers something, or it can be used to correct something inside the circuit to tell it that it is a state of a voltage. And then they're used also in analog and digital circuits that require precision references. So just basically a precision reference circuit. And finally, in precision current limiters. Precision current limiters. Let's assume, supposing you got a large voltage You put a Xena, then I'll use a PNP here. Then this output over here, this is actually equal to a constant current source. This is actually equal to a constant current source. So this current source will be limited to respect of the load that you put over here. I assume you call this one RB1. So that's a PNP transistor. I've done a mistake. There should be a resistance over here. Let's call this one RE. So the drop across the Xena is BZ. The drop across the base emitter junction of the transistor is VBE in general. If it is a silicon transistor, approximately 0.65 volts at room temperature. If it's germanium, maybe 0.1. So that the current which will be passing through if I put a load across the collector and the lower voltage, maybe 0 volts, the lower voltage, say let's call it 0 volts, then in general I will be equal to VZ minus VBE all over RE. So that will be the maximum current that we want to pass through that circuit. Where VBE, I said is 0.65 at room temperature. So that's the thing. So with that, we come to the end of this section. Unless there's any other questions on this circuit. Normally, it is not used because of its poor efficiency. Normally, it's not used. In fact, the only shunt regulator that we use commonly is this Xena. We design a Xena with correct biasing to give us a precision voltage across the Xena, which we'll use as a voltage reference. Okay, but to get an IC which has been designed by a company to perform shunt regulation is very rare because of its poor efficiency. When there is no load, ISH is still flowing, and therefore the efficiency is very poor. So any questions on this before we go to our next topic, which will be our last topic? Moses, any questions? Moses, you're not there today? You've already gone? So you people are not in class?
We're in class.
Yeah, I can see a door, but where's the CR? Moses, why are you? Switch on your mic. So become crafty. Okay, so we'll go to the next topic, which is normally my last topic, which is the series regulator. The series regulator. Remember, these are the three topologies or the three ways of implementation. We had the shunt, which we just done. Before shunt, there's a series. So series controller element is a series of the supply and the load. And then the last one, which will be your assignment, is the switching regulators. The simple implementation over here. But that's not all. So this is our series regulator. This is our series regulator. So this I'm calling it a practical series regulator. So you got an unregulated supply V1 on the left. You got a reference circuit over here, which comprises of this resistor written RA and VZ to give us a reference. Now the difference here, the voltage is connected to the positive. The reference voltage is connected to the positive of the error amplifier. And then R1 and R2 forms the sampling element or the output sampling element to give the error amplifier some feedback of what's happening in the output. You got your load over here, and then you've got your control element over here. Now in this case I've used 2 transistors, but you can also work with the one. It just depends on your design requirement. If you're using transistors connected this way, it forms a Darlington. And the property of a Darlington is that the current gain of the circuit is approximately HFE of transistor 1 times HFE of transistor 2. It's approximately equal to that. So this is just like one big transistor with a HFE equal to the product of the 2 HFEs. Now there's this resistance R over here. Actually, it's been put in the wrong place. This R should be near. This R should be near the supply voltage. It should be near the supply voltage here, not here. This is to depict the output resistance of your unregulated supply. If you look backwards into your unregulated supply, this R here is the output resistance of your regulated supply. So we want to be using it inside our equation. We want to be using it inside the equation. Although I've drawn it over here, but it's supposed to be somewhere here. The resistance in looking back into our unregulated power supply. All power supplies have got some internal resistance unless it's an ideal power supply, like the ones used in circuits. But most practical power supplies will have a resistance. Maybe it could be a milliohm or 2 milliohms or 10 milliohms. But there's some physical resistance seen going backwards. Okay. So this is our series power supply. It's called series because the control element, which is formed by Q1 and Q2, is in series with the unregulated power supply and our load. So now let's see how this circuit will work. How does it work? So let's assume the output voltage was initially at the optimum design voltage. And then, and use some colors here. So let's assume the voltage was originally your design voltage. Later on, we shall come to the working equation. So let's assume it was the correct voltage V naught you've designed it to. And then you increase the load. Let's assume you increase the load. So when you increase the load, this voltage will tend to go down. The original design voltage will tend to move down, and therefore the voltage at this point over here divided by R1 and R2 will also go down. And this voltage going down over here will be fed back to the minus input of the amplifier. The other side is fixed at Vz. And therefore the output will go up because you're feeding it to the minus input of the op amp. So it's inverted and amplified, and therefore the bias voltage that goes to Q1 and Q2 will increase, and therefore the drive current of Q2 will increase, which will increase the drive current of Q1, and this will tend to increase the voltage to compensate for the drop which was initiated by increasing the load. On the other hand, if the load voltage decreases, when initially it was at V0, and I decrease the load, the tendency of the output circuit is to output voltage is to increase, and therefore the voltage which is sampled will also increase, and therefore the voltage fed to the minus will increase, and therefore the output voltage of the op amp will now decrease because it's inverted, and therefore the drive voltage to Q1 will decrease, and therefore the drive current of Q2 will decrease. The drive voltage in this case will also decrease. So basically that's how this system works. Now let's do this mathematically. Let's do it mathematically. So I'll be using an arbitrary voltage V0 dash as my output of my op amp. So please go check in the class notes I posted that because what I've written here by pen in the drawing there could have been a mistake. So ensure that the output of our sampling element, our reference, is going to positive, and our sampled element from the output is connected to the negative of our error amplifier. So V0 dash is the voltage of our error amplifier, and V0 is our actual output voltage. So the voltage that is sampled back over here, the middle of R1 and R2, will be R2 over R1 plus R2 into V0. That is the voltage here. Okay, and we'll simplify it as beta V naught. Beta V naught, we'll just call it beta V naught, where beta is R2 over R1 and R2. Is the sampling fraction. Okay. Okay, so let's analyze this circuit. So if our output voltage is V naught, the voltage at this point will be beta V naught. Beta V naught goes to the minus terminal of our error amplifier, and Vz goes to the positive terminal, and therefore V naught dash. So if this has got a gain of AD, the difference gain is AD. This side is Vz, this side is beta V naught, and therefore V naught dash will just be equal to Vz minus beta V naught, all into brackets, AD. So that's how I'll get my first equation. So V naught dash will be equal to AD, Vref minus V naught into R2 over R1 plus R2, or simply put, it's AD Vz minus V naught into beta. So that is just what I was saying over here. So you got Vz on the positive side, beta V naught on the negative side. It's a difference amplifier, so the output V naught dash will be AD into brackets Vz minus beta V naught. That's how you get equation 2. And I've said that Vz is the same as your Vref, and beta is your R2 over R1 plus R2. Now also in this circuit, if you look at this circuit, the drop, if the transistors are working, there will be a drop VBE plus minus here, another drop VBE plus minus over there. So if we start at V naught, we climb through VB1, we climb again through VB2, we'll get V naught dash. So we can write V naught plus VB1 plus VB2 is equal to V naught dash. Okay, and if the transistors are the same, the silicon transistors, then you can just write V naught plus 2 VBE is equal to V naught dash. So that's what I've written over here. And also, V naught is VB1 plus VB2. Sorry, V naught dash is equal to VB1 plus VB2 plus V naught. Or we can write V naught dash is 2 VB plus V naught. Now, from our first equation over here, from equation 2, V naught dash was equal to AD into brackets Vz minus beta V naught. So let's substitute for V naught dash in equation 2 with equation 4. So if I do that, I'll get 2 VBE, which is the right-hand side of 4, plus V naught is equal to V naught dash, but V naught dash is equal to 2. And what is 2? 2 is AD, the brackets Vz minus V naught beta. So this is equation 2 here. So now all I have to do is solve for V naught. So we get the common terms together, and I'll put V naughts, terms of V naught on the left. So I've got one in equation 5, I've got this V naught over here. And then on the right-hand side of 5, I've got minus AD V naught beta. So if I bring it to the left-hand side, I get positive AD V naught beta. And from 5, I'll remain with ADVZ on the right-hand side, which is this term. And the other term I'll have from 5 is 2 VBE. So I'll bring this term to the right, and becomes minus 2 VBE. So now I'll make V naught the subject. So left-hand side of 6 can be written as V naught into 1 plus AD into beta is equal to AD VZ minus 2 VBE. Then I solve for V naught. So I'll divide the right hand of 7 by 1 plus AD beta. So I'll get equation 8, which is the first time the numerator is just the right hand of 7 AD VZ minus 2 VBE, which is this, all divided by 1 plus AD beta. So that's how I get equation 8. So next I'll simplify right hand side of 8 by dividing numerator, denominator by AD. So the first term in the numerator of 8, which is AD VZ, if I divide it by AD, I just remain with VZ. So that's how I get this first term in the numerator of 9. The second term, numerator of 8 minus 2 VBE, if I divide it by AD, I'll get this term over here, minus 2 VBE divided by AD. Now let's go to the denominator. In 8, I had a 1. So this 1, if I divide it by AD, I'll get 1 over AD. The next term in 8, in the denominator, AD beta, if I divide it by AD, I just remove the beta. So that is how I get 9. Now AD for most op-amps is greater than 1. AD is typically over 100,000. AD is typically over 100,000. So if you look at the numerator of 9, the term with AD, you get 2 VBE. Now VBE is a single VBE is about 0.65 volts. So 2 VBE will be approximately 1.3 volts, and if you divide it by 100,000, it becomes negligible. So this term in 9 is negligible. And similarly, this term in the denominator, 1 over AD, will be like 1 over 100,000. It's negligible compared to the fraction of beta. So equation 9 can just be simplified as Z divided by beta. But what was beta? Beta we said was R2 over R1 plus R2. This beta is not the gain of the transistor. This beta is the fractional gain, the fraction of the output voltage that is fed to the input of the op-amp. So beta was R2 over R1 plus R2. So that's how we get this other term of 10. And if you simplify this, we know it will simply be Z into brackets 1 plus R2. Sorry, 1 plus R1 divided by R2. And if you look at this equation 10 over here, you can see that V naught is independent of V in. V naught is independent of RL. V naught is only dependent on VZ, R1, and R2. So this equation also gives us how our regulator works. So if it's designed properly, if you increase the load or decrease the load, the output voltage will be constant. If the input voltage V1 increases or decreases, the output will still be constant. So this is how mathematically our regulator works. Now let's consider some of the design requirements of this circuit. So one requirement which is important is that the op-amp must be capable of delivering the base current corresponding to the maximum load at the minimum beta DC. Now this beta now is different. Beta DC here, this is like the HFE of Q1 and Q2. The smaller the beta DC, this beta now is the HFE of the transistors, the larger the current drive required from the op-amp. Now, typical dissipations of op-amps are approximately 300 milliwatts. Now, let's just go and check this data of this op-amp of Texas Instrument, just to shed some light on what I'm talking about here. Let's go to so this is internal construction of a Texas Instrument op-amp. So this is the output voltage. This is the output of our circuit. So you see there was some emitter resistance, like this emitter resistance is for protection. This emitter resistance here is for protection. Okay, so that when the drop across this resistor is approximately 0.6, or you can take 0.5 for cut-in voltage. Okay, the cut-in, there's a difference between the cut-in voltage, that's called the knee voltage. So when this voltage I put a different color so it's brighter. So when this voltage over here, the cut-in voltage of silicon, let's assume is 0.5 volts. You know, if you're to draw the transfer function of a transistor, the base of a transistor is something like this. And so this is the new voltage, and the cut-in voltage okay, so for most transistors, normally we'll bias the transistor maybe somewhere here. Okay, so that if you're designing an amplifier, okay, so this could be maybe, this could correspond to maybe 0.65 and 0.65 volts, depending on the temperature. Okay, so let's assume that the new voltage is our cut-in voltage, just to make life easy. So this could be maybe 0.6 volts. So let me use 0.6. Then it means that when this drop over here is 0.6, it means the current going to the load, because you'll be putting your load over here to the ground. So 0.6 should equal to your current I load, times this R protection, R9. So it's 25, not 20. Okay, I'll write it down here, 0.6 should be equal to IL times 25. What's happening to me today? So you can get that IL, that's the limiting current, will be equal to 0.6 over 25. That's in amps. So 0.6 divided by 25. My calculator is misbehaving. Okay, let's see if I can get the Microsoft one. So 0.6 divide 25, 0.24. So that's about, if you multiply by 1,000, 24 milliamps. So for this circuit, the engineers have designed it so that the maximum output voltage you can get from this op-amp is 26 milliamps. But you don't have to go here to calculate this. You can just go to the data sheet and the engineers will tell you the maximum output of this thing. Let's see if I can get the data sheet. Oh boy, I can't, they didn't give it. They didn't give the data sheet. Oh, it should be here. Okay, let's see. So from the Texas Instrument data sheet, they tell it comes in two packaging. The DAP and the TO99 package. This is a round one with metal. It tells you the supply voltages. You see, there were two types, the LM and LM41A and LM41C. With 1C, the supply voltage is smaller. Then the maximum dissipation of this circuit is 500 milliwatts. So that's the maximum you can dissipate. So power going into the op-amp times the current going into the op-amp should not exceed 500 milliwatts. They give you the operating temperature. So you can see that for the LM741 and 741A, you can go to very low temperatures. So if you're designing something that can work in places like Greenland or Antarctica, you can use this one. But for warm countries, you can only use 741C, which can only work from 0 to 70 degrees centigrade. They tell you the maximum junction temperature and soldering information. I wanted to get the maximum recommended currents. Okay, it's here. So look at this. The output voltage swing maximum is plus minus 15 volts. Of course, for you to get plus minus 15 volts, you got to use a VCC of at least plus minus 18 volts. And the output short circuit current at 25 degrees centigrade is 25 milliamps. So remember, for us, we were able to where's that thing? I lost it again. How come? Okay, I think. How come I didn't save it? Anyway, we were able, using the components which are shown in the internal circuitry, we got a current of 24 milliamps. And Texas Instruments tells you that the maximum output current of their op-amp is 25 milliamps from their data sheet. It's over here. Output short circuit current at 25 degrees centigrade is 25 milliamps. The one we computed from theory, we got 24 milliamps. So it means this op-amp cannot give you more than 24 milliamps at its output. Okay, so let's go back to class. So for example, let's wrap this information which is here now. Make it clean. Okay, so I've seen the mistake I did in the one I posted to you. Look at the base. This is supposed to, here is supposed to be negative. And this top one is supposed to be positive. So you can correct that. So the bottom one is negative. Okay, so if I was to use the Texas Instrument op-amp in this design, it means that the maximum current I can get over here is 25 milliamps. So let's say I'm supposed to design a power supply. Could somebody tell me, the yellow power supplies, what's the maximum current that they give? Is it 5 amps? Is it 10 amps? Somebody who is keen with the labs. Your lab power supplies, what's the maximum current they give? Anybody? No, Moses the CR is not there. Who is the lady CR? The lady CR can take his place. Lady CR, can you switch on your...
Hello?
Yes, Lady CR.
I'm here, Moses.
No, Moses, I've tried to look for you for a long time. Why have you
I
been?
was here even the other time, only that my network was down.
Okay, so the power supplies used in the lab, what is the maximum current they give?
What's the current? Current was...
Yes. They have a variable voltage. So what's the maximum current?
We are using 5 amperes.
5 amps.
Yes.
Okay, so that's most of those power supplies, they got a limit as to how much current they have. So for example, if the maximum current of your power supply is rated at 5 amps, so that is 5,000 milliamp hours. Then it implies that the maximum current that the op-amp can supply times HFE of your first transistor times HFE of your second transistor should give us 5,000. So 25 milliamps times HFE1 times HFE2 should at least give us 5,000. So this tells me that HFE1 times HFE2 will be equal to 5,000 divided by 25. So this should be 25 into 50 is 200. Okay, so this is the minimum total gain of the two transistors. Now, for most of the bench power supplies, Q1 is normally a power transistor. And power transistors, the most common power transistors for labs are normally like the 2N3055. Now these power transistors, and then you need a driver for this one, which is like BD. I think maybe 139. So this will be a driver. This is a driver transistor. So this will be like your Q2. And this is like your Q1. Okay, the power transistor must be connected to a heatsink. Now, if you go to the data sheet of the 2N3055, you'll find they might give you a HFE which ranges from maybe 20 to 70. We can check. Okay, so this one could have a HFE which the manufacturer says will range from maybe 20 all the way maybe to 70. And for BD135, it might increase maybe from 70 to maybe 120 or 130 or 140. Okay, let's just go to the internet and find out, and we can check the truth, which will set us free. Let's go to Ensemi. Ensemi is a Japanese manufacturer of transistors. So these are high quality transistors. So if you look at this one, now these are not the ones you'll find in Lethuli. The ones you'll find in Lethuli, there'll be copycats. So you can see here, current gain 20 to 70 at about 4 amps. So HFE is 20 to 70. Okay. And if you're designing the power supply If it's an exam problem, you got to go to some other data so that you understand the maximum voltage you can put across the collector emitter, and base is open is 60 volts. So this transistor, you're only allowed to put maximum of 60 volts. Okay, so let's look at the other one. It didn't give me BD139. On semi also produces BD139 here. So from BD135 all the way to 139. So the packaging is like this. It's called TO126 packaging. So you can also put it to a heatsink. One side is metal. So they give you the maximum absolute rating for this one. So this one's the maximum voltage you can put across them. If it's 139, you can put 80 volts. But to be safe, use, it's 80 volts. Whether the base is open, you can use 80 volts. And then you can see the power dissipation of this one is 20 watts. I forgot to show you the power dissipation of the other one. So the power dissipation of this one at 25 degrees centigrade. This is another problem students always have a problem with. Even I see in the projects when they design things, they'll use transistors and they don't go and check the data sheet, and therefore do not design for heat sinking. The manufacturers will always tell you that they'll give you the maximum rating at 25 degrees centigrade. Now, as you continue to pass current through the transistor, it warms up and you can get the power by just multiplying the current through the transistor times the voltage across the transistor. Will give you the power dissipate, the transistor dissipating inside the circuit. But since the metal part of the transistor is so tiny, the temperature will start to increase very rapidly. The temperature will start to increase very, very rapidly. So if you don't take care of the heat sinking, for example here, and this is what is known as the thermal resistance. It's supposed to be here. They normally give you what is known as the thermal resistance of the transistor, which is how many degrees centigrade the body of the transistor will rise, or the small metal part of the transistor will rise for each watt. Since I can't see it here, let's go back. So this is the other data that we were looking for. The other data, you can see HFE. I don't know what is this classification number 6. This may be some which are sorted out. The factory will sort out some of them. So if you just go to the shop and buy a BD139, it can be any of these classifications. And they charge you more, the more the current gain. So you can see this classification, which they're calling number 6, the HFE will range from 40 to 100. And this classification number 10, the HFE will range from 63 to 160. So they charge different prices because they've got to put somebody, an employee, to sort them out and test them. And then number 16 will be from 100 to 250. So if you just go to the shop like Lituli and buy this transistor, most probably because these guys go to China and get the cheapest transistors, it could be this one. most likely because it will be cheaper, so they can make the maximum profit. But let me look for this thermal resistance thing, which is very important. I can't see it here. It should be here somewhere. They just put device dissipation. So for example, this transistor, you can see the PC, they're calling it the device dissipation at 25 degrees centigrade. The maximum power the device should dissipate is 12.5 watts. That's the maximum. And you go to derate it as the temperature increases. And you're told here the temperature should not exceed 150 degrees centigrade. Actually, most silicon devices, you don't want them to be operating beyond 55 degrees centigrade. Otherwise, the life would be very short. Now, they're not giving us it's known as the thermal resistance. I'm looking for that one. Let me go to the beginning and see. It's not there. Okay, let's go back to the other one. On semi, let's go back to the power transistor. So this is current gain from 20 to 70. When I see is that okay, for this one it's given. Can you see this? The total power dissipation at 25 degrees centigrade. So this transistor is rated at 115 watts at 25 degrees centigrade. So if you can maintain that temperature of 25 degrees centigrade, then you're allowed to dissipate this power through the transistor. Otherwise, you're told to derate above 25 degrees centigrade at a rate of 0.657 watts per degree centigrade. So this 0.657 is actually how much the temperature will increase if you don't put a heatsink on the device. So you go to derate it at, for each degree centigrade rise, you go to decrease the power by 0.657. Okay, so for example, supposing the temperature rises by 10 degrees, then I go to derate it by 6.5 watts. If the temperature rises to 100 degrees, I'm going to derate the power going to the device by 0.65 times 100, which is 65 watts. So it means your device now, maximum power allowed will be 115 minus 65 watts. Okay, normally they show you a derating curve. Yeah, this is the derating curve. This is what I was looking for. This curve over here is called the derating curve. Okay, so at 25 degrees centigrade, you can operate your device at 115 watts. If the temperature increases to 50 degrees, your transistor now will only be rated 100 watts. If the temperature increases to, say, 100 degrees, your transistor is now rated for only like about 60 or 70 watts. Okay, but normally we don't want transistor to be operated beyond 50. If you want the life of the transistor to be long, okay, you normally want to operate it below 55. Now, this transistor is normally used for things like audio amplifiers, up to 100 watts per channel. So I hope you've understood that. Okay, so we're looking at the current gain. This one we got 20 to 70. And the other one, we got the current gain to be what? The lowest one. Forty to 100. Okay, so now let's get back to class. So since you do not know when you go to the shop which one you're going to get, so the driver, the HFE can be 40 to 100. And for the power transistor, 20 to 70. And these are the HFE. So we normally use worst case design. So let's assume the first transistor had a HFE. This Q2. So let's assume Q2 and the HFE is 40. Because the manufacturer says it can vary from 40 to 100. So you can't assume you got the one over 100. Similarly, let's assume, and that is the safe assumption. That is the safer assumption. For Q1, the power transistor, you got HFE of 20. Okay, so we can write HF. Charge of my pen is finished, but I got another pen today. So HFE 1 times HFE 2 will be equal to 40 times 20. Okay, and this is actually equal to 800. So let's test if you have to put those transistors here. Now, Texas Instrument tells us the maximum current that their op-amp can supply 25 milliamps. And therefore, IL max, which is our load current, IL max will be op-amp output, which is 25 milliamps, times the gain of the two Darlingtons. Gain of the two Darlingtons is 800. And this will be equal to, my calculator is dead today, I don't know what's wrong with it. Okay, let's try it. I'll go back to form standard 7, 25. I'll put 2 zeros, then multiply by 8. So this is 0, 0, 40, 16 is 20. So it's 20 amps. I hope I'm correct. $25 milliamps times 800 is 20,000. Somebody check if you got a good calculator. I don't want to go to Microsoft. Okay, let me see. Where's my Microsoft thing? It's wasting time. But I think it's correct. I think it's correct. I'll get the, it's not correct. It's not correct. I still have done the mistake. So I put the 2 zeros on the 25. So I got 25 and 2 zeros. And I multiply by 8. So that's 0, 0, 40, 16, 20. Yeah, it's correct. So this is actually 20 amps. Okay, so it means in the design, in this design over here, it will easily give 5,000 amps at the output. If I use the Texas Instrument 741, and if I use these two transistors that I gave, the BD139 and the 2N3055, if I pick them at random, or I was given at random in the shop, and put them over here, they'll be able to give me up to 20 amps. So I can design a power supply whose output is up to 20 amperes. How did I get the 20 amperes? I get the maximum current that the op-amp can supply from the manufacturer, then multiply it with the worst case gain of the first transistor times the worst case gain of the second transistor, which is a power transistor, and it will supply for me the current. So I hope that is understood. Now let's continue with our notes. So we've done this design over here. So we're considering the design requirements. So number one is that the op-amp must be capable of delivering the base current corresponding to the maximum load. Okay, so how do you get to the op-amp requirement? To get the op-amp requirement, supposing IL is the load current. All right, so IL max is your design. Then IL max divided by HFE, let's call it total, should be equal to I'll call it I out of op-amp. Now, supposing in this design that we just considered here, supposing I just use one transistor, one power transistor. Supposing I just used one power transistor instead of using two. Okay, instead of using two, I just used one power transistor. So this circuit over here would look like, I think one of the earlier circuits I did, it would look, sorry, where is it? I think it's in the exercise. In the exercise. Hey, hello, Moses. Can you hear me?
Yes, we can.
Can you see the presentation?
Yes.
Yes.
My network, something went wrong with my network. Yes, wait, I want my student computer to also be connected. It went off also. Now I'm in a very slow speed network. My high speed network, something has gone wrong. So now things will be reacting very slowly. So what I wanted to say is this, that supposing I'd used only one transistor, supposing I'd used only one transistor, only Q1. Let's assume I'd only used Q1. So the output of my op-amp was connected to only one transistor, Q1. And I'm using a Texas Instrument op-amp, which can supply 25 milliamps. Then it means the maximum current my circuit will be able to give to the load will only be 25 milliamps times 20, which is 500 milliamps. Okay, so it means that if I'm to design a series regulator with a Texas op 741, which can only supply 50 milliamps, and instead of using a Darlington pair, what I've done is just use one power transistor, in this case Q1. Then Q1, if I'm using the 213055, we'll have a manufacturer says it will range from 20 to 70, but I'm not sure which one I get when I go to buy one. So we design for the worst case and use 20 as the HFE. So 20 times 25 milliamps will tell me that my circuit will only be able to provide 500 milliamps. So you can see the advantage of using a Darlington pair. With the Darlington pair, if I get a driver like the BD139, whose HFE can range from 40 to 100, and I get a power transistor at the output whose HFE can range from 20 to 70, even if I use the worst case design, HFE of the driver transistor can be taken as 40, HFE of the power transistor can be taken as 20, and 20 times 40 will be 800. And 800 times the drive current from my op-amp will now be, we got it as I think 20,000. So that is the best way to design an output stage or the control element of the series power supply. Now, most of our lab power supplies are actually obtained from this. They actually use this exact circuit, and then on switching ones onto the heavy transformers. So we have two of them, one from 0 to maybe a positive value, maybe 30 volts. And then we use an opposite design, we're using PNPs and put it at the bottom. So we got 0 to maybe plus 30, 0 to minus 30. And we can put a resistor here in the middle over here. A pot, actually, we normally use a pot over here so that you can increase this voltage maybe from maybe 3 volts all the way to maybe 30 volts. Okay, and they're synchronized. There's another similar circuit like this, but with PNPs on the bottom side. This is what I mean. I don't know, some of you will, if you'll get it. So this would be one. This is 0 volts. So this is the output, and this will be another. So this can be maybe plus 40 volts here, minus 40 volts here. So this one will give us our minus voltages. So we've got a sampling element with a variable. I don't know, when time is up, I tend to make mistakes. So these two ports are synchronized. They're ganged in one. So this becomes here 0. So here maybe you can get plus 15 volts. Here you can get minus 15 volts. So you've got an identical circuit. Let's call circuit A and circuit B. Circuit A is like the one we're using today, and circuit B is identical to this one, circuit A, but only we use PNP transistors instead of using NPN. So that way you get a power supply which can with a variable. It's got a variable voltage. You can vary maybe from 1 volt all the way to 15 volts, or 1 volt to maybe positive 30 volts. And also the opposite side has got 0 to maybe minus 30 volts. So that is how we design a series regulator. Moses, do you have a class after this? Moses, do you have a class after this?
Yes, there is a power electronics class.
Oh, there's a power electronics class. Somebody has written me a note over here. I don't know what it is. Ochor Samuel, which vendors have space-grade electronics for outer space missions, and how does the design of space qualified electronics differ from the rest? If you're going to space, you need special electronics, or you protect your devices. You protect your electronics. You protect your electronics. Okay, so you got to go to most of the semiconductor companies. They can make for you specialized components at a cost. Yeah, they make for you specialized components at a cost. Okay, but this will be the big companies that manufacture semiconductor devices. Okay, people like Toshiba, people like Siemens. Okay, Texas Instruments, by the way, is young. It's not very old as these other companies. And even people like Philips. Philips, in fact, in electronics, long time ago, Philips was the world leader. Something happened to them. Said that they sold most of their divisions. So I hope I've answered your thing, your question. They're cheap things, for DIY, cheap things for slightly better things for home use. And then there are things for professionals, which you got to pay more. You got to pay much, much more for them. Okay, I'll stop over here. And Moses, you tell me when we want the CAT. Okay, we finished most of the things. Actually, today I wanted to complete this section so that I can leave you people to study for the CAT, because all that remains now was just this small section to calculate the efficiency. Calculate the efficiency.
Okay.
And then
I'll be
conclude.
calling you now. I'll call you to agree on the date.
Okay. So what's remaining is just 1 hour. 1 hour, and then we complete everything.
Is there any possible way you can have a takeaway?
No. This is Nairobi University, but takeaways for Polytechnic.
Okay, it's okay. We agree.
Okay, thank you.